Imagine you have a coin. You flip it, and while it's in the air, it's both heads and tails simultaneously. Not one or the other, both. Then you catch it and look. At that moment, the coin suddenly becomes definitively heads or tails. Your act of looking forced the coin to choose. Before you looked, it existed in a ghostly superposition of both states. This sounds insane, but it's exactly what quantum mechanics says happens at the subatomic level. An electron doesn't have a definite position until you measure it. A photon isn't polarized until you check. A particle exists in multiple states at once, superposition, until observation collapses the wave function and forces nature to pick one outcome. This is the measurement problem, and it's the deepest mystery in quantum mechanics. After a century of debate, physicists still don't agree on what measurement actually does. Does observation create reality? Is consciousness required to collapse the wave function? Do all possible outcomes happen in parallel universes? Or is the wave function just information in our heads, not physical reality? The implications are staggering. If observation creates reality, then before humans evolved, was the universe in superposition? Did the moon not have a definite position until someone looked at it? Einstein hated this. He famously asked, "Do you really think the moon isn't there when nobody looks?" But quantum mechanics suggests he might be wrong. Welcome to the measurement problem, where reality depends on observation, where particles are waves and waves are particles, and where the line between observer and observed dissolves into quantum uncertainty. Quantum mechanics emerged in the early 20th century as physicists tried to understand atoms and light. Classical physics failed at the microscopic scale. Light sometimes behaved like waves, sometimes like particles. Electrons exhibited wave interference patterns. Matter wasn't solid. It was probabilistic, fuzzy, uncertain. The mathematics worked brilliantly. Schrödinger's wave equation predicted atomic behavior with stunning accuracy. But interpreting what the math meant philosophically proved impossible. The wave function, denoted psi, describes a quantum system. For a particle, psi gives the probability of finding it at different locations. Before measurement, the particle has no definite position. It's smeared out in space, existing in superposition. This isn't ignorance. It's not that the particle has a definite position and we just don't know it. The particle genuinely has no position until measured. How do we know? Through interference experiments. The most famous is the double-slit experiment. Fire electrons one at a time through two slits. Each electron passes through both slits simultaneously, interfering with itself like a wave, creating an interference pattern on a detector screen. But the moment you try to detect which slit the electron goes through, the interference vanishes. The electron behaves like a particle, going through one slit or the other. Your measurement changes the outcome. This is observer effect. But it's not just disturbance from clumsy measurements. Quantum mechanics says the electron truly is in superposition, passing through both slits, until measurement collapses it into one definite state. This led Niels Bohr and Werner Heisenberg to develop the Copenhagen interpretation in the 1920s. The Copenhagen interpretation says the wave function represents our knowledge of the system. Before measurement, the system doesn't have definite properties. Asking where the electron is before measurement is meaningless, like asking what color Wednesday is. Only upon measurement does the system acquire definite properties. Measurement collapses the wave function from superposition to a single outcome. Bohr famously said, "There is no quantum world. There is only an abstract quantum description." Reality, in Bohr's view, only emerges through measurement. But this raises profound questions. What counts as a measurement? Does it require a conscious observer? Or does any interaction with the environment count? And what is wave function collapse? Is it a physical process? If so, what causes it? Schrödinger's equation, which governs quantum evolution, is deterministic and smooth. There's no collapse in the equation. Collapse is added by hand, an extra postulate. This bothered many physicists, including Schrödinger himself. To illustrate the absurdity, Schrödinger proposed his famous cat thought experiment in 1935. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, breaking the vial and killing the cat. Quantum mechanics says the atom is in superposition, decayed and not decayed, until measured. Therefore, the cat is also in superposition, dead and alive, until you open the box and observe. Only then does the cat become definitively alive or dead. This seems ridiculous. Cats aren't both alive and dead. They're macroscopic objects with definite states. Schrödinger intended this as a reductio ad absurdum, proof that quantum mechanics, taken literally, leads to nonsense. But instead of discrediting quantum mechanics, the cat highlighted the measurement problem. Where does superposition end and definiteness begin? At what scale does quantum weirdness give way to classical reality? This is called the quantum to classical transition. One answer is decoherence. When a quantum system interacts with its environment, air molecules, photons, thermal vibrations, superpositions become entangled with countless environmental particles. This effectively destroys interference, making superpositions unobservable. Decoherence happens almost instantly for macroscopic objects. A cat interacts with trillions of air molecules per second. Superposition decoheres in a tiny fraction of a second, long before you open the box. Decoherence explains why we don't see quantum weirdness in everyday life. But it doesn't solve the measurement problem. Decoherence makes superpositions unobservable, but mathematically they're still there. The cat is still in superposition, just entangled with the environment. You still need wave function collapse to get a definite outcome, and the collapse remains mysterious. Einstein despised the Copenhagen interpretation. He believed in an objective reality independent of observation. He argued that quantum mechanics is incomplete. There must be hidden variables determining outcomes. In the famous Einstein-Podolsky-Rosen paper of 1935, Einstein proposed that particles have definite properties all along, governed by hidden variables we can't access. Quantum mechanics only describes our incomplete knowledge, not reality itself. But in 1964, physicist John Bell proved that hidden variables couldn't reproduce all quantum predictions. Bell's theorem showed that any hidden variable theory must allow non-local influences, spooky action at a distance, as Einstein called it. Experiments confirmed Bell's predictions. Quantum mechanics is correct. Hidden variables, if they exist, require faster-than-light connections. This is deeply strange. It means quantum entanglement, particles correlated across arbitrary distances, is real. Measure one particle, and the other instantly reflects the result, even light-years away. Einstein's local realism is wrong. Reality is either non-local or not real until measured. This opened the door to radical interpretations. Hugh Everett proposed the many worlds interpretation in 1957. Everett said, wave function collapse doesn't happen. Instead, every quantum outcome occurs in a different branch of reality. When you measure Schrödinger's cat, the universe splits. In one branch, the cat is alive. In another, the cat is dead. Both outcomes are real. You just experience one branch. From your perspective, collapse happens. But from a universal perspective, all outcomes exist in parallel. Many worlds avoids the measurement problem by eliminating collapse. The wave function never collapses. It just keeps evolving, branching into countless parallel universes. This is mathematically elegant. Schrödinger's equation governs everything. No special measurement postulate needed. But it's ontologically extravagant. You must accept that every quantum event spawns universes. Every decision, every particle interaction, reality branches. Most physicists find this too radical, but many worlds is increasingly popular, especially among quantum computing researchers. Another interpretation is the pilot wave theory, developed by Louis de Broglie and later David Bohm. In this view, particles always have definite positions, guided by a wave, the pilot wave. The wave function isn't the particle. It's a field that pushes the particle around. Measurement reveals the particle's position, which was always definite. This restores realism. Particles have trajectories. But the pilot wave is non-local. It instantly responds to changes everywhere. And the theory reproduces quantum predictions exactly, making it empirically equivalent to standard quantum mechanics. It's a matter of philosophical preference. Do you prefer Bohr's observer-dependent reality, Everett's infinite branches, or Bohm's non-local pilot waves? All fit the data. Some physicists embrace the participatory universe concept. John Wheeler suggested that observers don't just reveal reality, they create it. Wheeler's delayed choice experiments show that decisions made after a photon has passed through apparatus can retroactively determine its behavior. This suggests the past isn't fixed until observed. Reality is participatory. Observers and observed are co-creators of existence. Wheeler even speculated that the universe creates itself through observer participation, a self-excited circuit. This sounds mystical, but Wheeler was a rigorous physicist. He believed quantum mechanics hints at something profound about the nature of existence. Then there's the role of consciousness. Eugene Wigner proposed that consciousness collapses the wave function. In Wigner's view, physical interactions aren't enough. Only a conscious observer can actualize reality. Wigner imagined his friend observing Schrödinger's cat while Wigner waits outside. From the friend's perspective, the cat collapses into alive or dead. But from Wigner's perspective, the friend and cat remain in superposition until Wigner himself observes. This creates a hierarchy of consciousnesses. Whose observation matters? Wigner suggested consciousness is fundamental, not emergent. Without consciousness, reality remains quantum, indeterminate, potential. Most physicists reject this. Consciousness seems too vague and subjective to play a fundamental role in physics. But some, like Roger Penrose and Stuart Hameroff, argue that consciousness involves quantum processes, perhaps explaining both measurement and subjective experience. This remains highly controversial. The measurement problem also connects to interpretations of probability. In the Copenhagen interpretation, quantum mechanics gives probabilities for measurement outcomes. But what does probability mean? The frequency interpretation says probability is the long-run frequency of outcomes. But for a single event, what does probability mean? The Bayesian interpretation says probability represents degrees of belief. The wave function encodes information, and collapse is updating beliefs based on new data. This is called cubism, quantum Bayesianism. In this view, the wave function isn't physical. It's a tool for making predictions. Different observers can have different wave functions for the same system, reflecting different information. There's no objective wave function, no objective collapse. Measurement is updating personal information, not a physical event. This dissolves the measurement problem. There's nothing mysterious about collapse. It's just learning. But critics argue this is too subjective. It makes quantum mechanics about belief, not reality. And it doesn't explain why quantum mechanics works so well if it's just belief. Another approach is relational quantum mechanics, developed by Carlo Rovelli. Rovelli says quantum states are relational. They're not properties of systems in isolation, but properties of interactions. Different observers can assign different states to the same system, and both are correct relative to their perspective. There's no absolute wave function. Everything is relational. Measurement isn't special, it's just interaction. This fits with relativity's insight that space and time are relational, but it abandons the idea of objective reality independent of observers. The measurement problem also relates to quantum Zeno effect. If you measure a system continuously, you prevent it from evolving. Frequent measurements freeze the system in its initial state. This is experimentally confirmed and used in quantum computing to protect qubits. It shows that measurement isn't passive observation. It's active intervention, shaping quantum evolution. Some philosophers argue the measurement problem is a pseudo-problem. Physicist N. David Merman said, "Shut up and calculate. The math works. Don't worry about interpretation." This pragmatic stance is common among working physicists, but it avoids deep questions. If we don't understand what measurement does, we don't understand quantum mechanics, and quantum mechanics describes all of reality. Ignoring interpretation means ignoring the nature of existence. Recent experiments test the boundaries. Delayed choice quantum erasers show that decisions made after a photon is detected can retroactively change its past behavior. This challenges our notion of time and causality. Quantum teleportation transfers quantum states across space without the state traveling through intervening space. This challenges our notion of locality, and macroscopic quantum superpositions are being created, molecules, even small diamonds, pushing the quantum to classical boundary. Yet we still see no definitive collapse, no clear line where quantum becomes classical. This suggests the measurement problem isn't about scale, it's about interpretation. So where does this leave us? After a century, the measurement problem remains unsolved. We have interpretations, Copenhagen, many worlds, pilot wave, cubism, relational, but no consensus. Each resolves the problem in its own way, but at a cost. Copenhagen sacrifices realism. Many worlds sacrifices uniqueness. Pilot waves sacrifice locality. Cubism sacrifices objectivity. Relational quantum mechanics sacrifices observer independence. Which cost is acceptable? That's a philosophical choice, and it has implications. If many worlds is true, every decision spawns universes. If consciousness collapses wave functions, minds are fundamental to physics. If cubism is true, reality is subjective. If Copenhagen is true, reality doesn't exist until observed. The measurement problem forces us to confront the nature of reality itself. Is there an objective world independent of observers? Or is reality participatory, co-created by observation? Can science describe reality as it is, or only as it appears to us? These aren't just abstract questions. They shape how we understand quantum computing, quantum cryptography, and the quest for quantum gravity. They inform debates about consciousness, free will, and the limits of knowledge. And they challenge our deepest intuitions about existence. Quantum mechanics works. It's the most successful scientific theory ever. But we still don't know what it means. And until we solve the measurement problem, we won't truly understand the universe we inhabit. Perhaps future physics will reveal a deeper theory, quantum gravity, a theory of everything that resolves measurement. Perhaps consciousness studies will uncover a role for minds in physics. Perhaps we'll accept that reality is genuinely indeterminate, probabilistic, observer-dependent. Or perhaps the measurement problem is unsolvable, a fundamental limit to human understanding. Either way, the mystery endures. And it reminds us that reality is stranger, deeper, and more wonderful than common sense suggests. Every time you observe something, anything, you're participating in the greatest unsolved problem in physics. You're collapsing wave functions, actualizing reality, shaping existence itself. Or maybe you're just updating your beliefs, or splitting universes, or riding pilot waves. The truth is, We don't know. And that makes quantum mechanics the most fascinating, frustrating, and profound theory ever devised.